Hello, everybody. Good afternoon. Again, my name is Dennis Hong. I'm a professor and the director of ROMELA, the Robotics and Mechanisms Laboratory at UCLA. At UCLA ROMELA, we do a lot of different type of research and development in robotics. We're one of the early pioneers in autonomous vehicles. In 2007, at DARPA Urban Challenge, we placed third place. We come up with all different type of mechanisms: 3-leg, 4-leg, 6-leg robots, chemically actuated robots, wheel-leg hybrid robots, and many, many different type of things. However, in the past 10 years, decade, we've been focusing more on humanoid robots. You probably have one of our robots in your lab. The research and development open source robot, Darwin OP, funded by National Science Foundation. Charlie, the fully autonomous soccer playing robot, is also the RoboCup world champion. Thor RD for disaster relief, one of the finalists in the DARPA Robotics Challenge. Thor, a humanoid robot that uses series elastic linear actuators, and many, many different type of robots, including Sapphire, the shipboard autonomous firefighting robot funded by the Navy for fighting fires and Navy ships. And we have many, many different type of humanoid robots. However, the past decade, we've been doing a lot of research and development in humanoid robots, and I'm starting to realize how difficult this really is. Humanoid robots, they're great. In science fiction, this is what we imagine, but they're too unstable. They constantly fall down. They're too slow. They walk like this kind of pace. Of course, most of the recent humanoid robots, there's fantastic robots that are starting to solve these two problems. But even yet, still, they're too expensive, they're too complex, and they're too expensive. But we do need these type of bipedal robots. So what do we do? Now, bipedal locomotion. We walk with 2 feet all the time, right? But how come it's difficult to implement this on robotics? So one thing I found out was this. This is fascinating. One of the reasons why bipedal locomotion robots are difficult is because the distance between your left and right leg. Because your leg moves up and down, forward and backwards because of distance, it creates this unwanted twisting moments, and that's why robots fall down. Now, this is a video of a competition called Robo1. It's a very popular robot competition. Now, these robots are mostly developed by hobbyists, not researchers, remote control. But if you look at them, they are very stable, they walk fast, and they don't fall down. It's amazing. Now, if you look carefully, how do they walk? They walk sideways. Because if you walk sideways, your left and right leg, they align, so you don't get this twisting moments. Now, for example, I got this inspiration from fencing or ballet. They always walk sideways. So if you walk sideways, it's stable. Problem solved. Now, the problem of walking sideways is that you don't really get to use your knees, right? So what do? We do this. Okay, if we're gonna do this, why don't you make this forward and do this? So it walks like this. Okay? It gets weirder. Now, if you walk like this, you're not really using your feet and ankles. So what do? We get rid of our feet and get rid of our ankle. If you're going to make changes, let's make more changes. The shin, we're going to change to something. I'm going to talk about this why, but we change the shin. Let's make more modifications. We change the head, and it becomes something weird. And I'm very excited to show you our new robot called NABi, non-anthropomorphic biped. As it says, it's a 2-leg robot that does not look like a human. So how does it walk? It walks like this. Simple, stable, low cost, very simple. It walks like that. Now, I briefly mentioned about a robot called Sapphire for firefighting on military ships. If you've been onto a Navy ship, when you open the door, it has a very high door seal. So for the Sapphire project, to go over it, you had to brace and do something like this, which was very, very difficult to do. Now, if your robot doesn't have to be in the human configuration, we can do something like this. Rotate the knee 360 degrees. Brilliant. Our robots can climb steps, but it's difficult. So now we do something like this. Now, is this all animation and simulation? No. In 2 weeks, from the idea to analysis to implementation, in 2 weeks, we build our first prototype, and you haven't seen anything like this.
You're wild.
It can show emotion by motion. If you meet a NABi for the first time, he's very happy to see you. It's like, hello, everybody. My name is NABi. Right? It can also hop and jump using the spring-like leg. If you have time, we'll talk about this, but it can jump and hop like this. It's a very interesting robot. It solves a lot of problems. So this is NABi. Would you like to see NABi? All right. Do we have NABi? All right. Bring it over. So what you see over here is our first early prototype NABi. Okay, just going to do a quick walk, just make it walk a little bit. It's very, very stable. I want to emphasize that this is a fully open loop. There are no sensors on it. Even with open loop, it can walk very, very stable. Now, can you imagine by having an Ironman closing the loop, this will be able to walk on uneven terrain and do many, many things. Thank you very much. So with this robot, can we continue the slides, please? Yeah. Our vision is to use these for many different applications. For example, autonomous car pulls up and it wants to deliver a package. What do you do from the car to the actual person? Our robot walks like this. The head opens up, picks up the package, and puts his head, which means that we need to have arms, right? Now we have arms, so let's use them as limbs, so that it walks up to the sidewalk. It can jump, hop like this, right? We have a new locomotion method called scrambling walk for uneven terrain. Climb upstairs, use the limbs as hands to open a door. In a hallway, lift your arms, and it becomes a humanoid form, and then deliver the package. So to do this, we need to have two limbs. Thus, we developed a new robot called ALPHRED, autonomous leg personal helper robot with enhanced dynamics. And we have ALPHRED on stage as well. So this is ALPHRED. We call that 4 limbs, not legs, not arms, because these limbs can be used for both locomotion and manipulation. We call this multimodal locomotion because it has many different ways. Oh, by the way, if you hear the sound, I don't know if you can hear it. This is not an internal combustion engine. When you do robotics research and development, you need to monitor a lot of parameters. In this case, you want to monitor the current. So we have a speaker. Do you hear it? It's engine sound, that's actually the current draw. So as you can imagine, it can have a wide sprawl quadruped walking. So wide sprawl, stable but slow. Now, if you want to go really fast, it changes configuration to more like a dog or a horse, and you can walk really. Don't make it go too fast. We don't have a lot of space. Okay, make it go run this way a little bit. Dynamic quadruped walking. Okay, good. All right, cool. And then we haven't implemented just yet, but we'll be able to do this and do a somersault kind of motion as a wheel. And if you fold his legs like this, it becomes more of a humanoid type bipedal walking. And of course, if you lift this arms like this, it becomes like the NABi type of locomotion. Cool, thank you very much. So this is ALPHRED. Cool, let's have the slides back up. Thank you. So we talked about different type of configurations, but another important thing is the actuator. Most of the robots that exist today use electric motor with a high geared, like a harmonic drive. So these are not back drivable. These are stiff, position controlled, stiff. And that's good if you're doing like an automation, if your assembly talks, we want to have an accurate motion. That's great. But if you want to have these type of leg robots walk on uneven terrain, you need something different. You need to have an actuator, like a muscle, that's compliant, and you can change the position and the stiffness or the force. Thus, we developed a new type of actuator called BEAR. I'll skip this slide for a second. Okay. This is a new type of actuator. So there's a lot of things going on. Just focus on this guy. You see this like double tuna can type kind of thing? This is the BEAR actuator. BEAR stands for back drivable electromechanical actuator for robots. So this is the actuator, and we just have a simple arm attached to it so you can see it. So if this is a regular motor with a gear, of course you can move it, but it's really stiff. Can I change it? So not just by software, you can change a lot of parameters. For example, it's damped, right? There's damping, right? It's damped. Now we can change it as a spring, right? And then we can change the stiffness to much stiffer, right? And then if you want to make it move, we can make it also move because it's an actuator. So this is a revolutionary technology that we developed. You can change the damping and all the physical properties. Cool. Just to show you how strong this is, we quickly build a stand. So as you can see, this is a single actuator. We build a single leg so it can make it jump. Oh, by the way, quickly, this NABi, everybody loves this face. Do you see this? The reason why I put this face is because before we had this, everybody thought the robot's walking sideways. But because this is actually forward and backward, we put the face so, this is forward and backward, right? So we have a box here, so let me see. I have a Sharpie here. Let's actually draw something over here. Right. Let's give it a face. Does it look similar to that? Okay? All right, so we're just going to demonstrate it jumping. By the way, we're not going to go full power today. Cool. Do you want to make it stronger a little bit? There you go. Yeah. Cool. A little bit stronger? No? Okay. But it actually goes up to over here. Right? So this is a revolutionary new technology called bear actuator. Let's pull up the slides. If you can have the slide in the background, please. So I'll skip this. I've demonstrated this jumping too. It goes way up high up over there. Okay. And of course, it's very accurate in motion and very, very fast as well. We're trying to, so we built a robot leg with this actuator to show you how fast it is and how accurate it is. Of course, you can change the physical property like damping and those kind of things. Is that cool? All right. So I am very excited to show you for the very first time, this is NABi ALPHRED version 2. So think of these robots, but with this bear actuator. As a matter of fact, we finished assembly 3 days ago. I'm not kidding. And 2 days ago, it stood up for the very first time. And this is the very first time we took it out of the lab. So you're seeing it for the very, very first time. So it's not going to walk just yet, but I think it can stand up and do something. By the way, it's a lot of things happening. Okay, so let's make it stand up. Okay, as I mentioned, by software, it can change a lot of the parameters. Let's make it stiffen the legs just to show you that it's a very stiff robot, which is more the conventional robots, right? But we can also change the compliance. Let's make it a little bit, give it a little more compliance. Okay, now it's compliant, right? See? And we believe that this is a breakthrough. So combining the bear actuator you've seen the jumping and these robots, this robot will be able to jump, roll, and do all these kind of crazy stuff, and we're very excited. Cool. I think we're running out of time, so, okay. All right. Thank you very much. So this is the version 2. And I can't wait to show you the next generation of robotics. Thank you very much.